This is GeologyBites with Oliver Strimple. Plutons are bodies of igneous rock that crystallize from magma at depth below the surface. But even though the magma never makes it to the surface, it still has to travel many kilometers up from its source near the base of the crust to the upper crust, where plutons form. How does it make that journey, and what is the resulting structure of plutons and the intrusions that feed them? Keith Klepeis is a field geologist who studies such questions. Recently, he has focused on one region in particular that provides an exceptional window into the origin, evolution, and structure of plutons, the southern Fiordland region of New Zealand's South Island. He is a professor at the College of Arts and Sciences at the University of Vermont. Keith Klepeis, welcome to GeologyBites.
Thanks very much, Oliver. I'm happy to be here.
In what tectonic contexts do plutons form?
They form in a variety of different environments, but one of the most common is above subduction zones. And above a subduction zone, when it goes beneath a continental plate, forms a Cordilleran-style magmatic arc. And we see those at the surface, say in the Andes or the Cascades, by a series of volcanoes. But if you think about what's below those volcanoes, there are these magma chambers that are made up of individual plutons and intrusions, and those are the parts that we're trying to study in this project.
Where do we find the most prominent plutons that are exposed at the surface today?
Well, there's a variety of different environments. Usually you have to look at ancient systems, so systems that might have been active tens to hundreds of millions of years ago. So for example, in the Andes, especially the southern part, there is this very large structure called the Patagonian batholith. And that was one of these large bodies of igneous material that fed volcanoes at the surface at one time, but that surface material has been eroded. And there's a bunch of other places. The Cascades in the United States is another place, and New Zealand has a wonderful deep exposure in the southwest part of the South Island called the Median batholith, and that's the one we're looking at.
Let's talk about the processes that lead from the subducting slab to the formation of magma at the base of the crust, and then to the eventual emplacement of a granitic pluton. Let's start with how the magma forms at the base of the crust.
So that begins with the process of subduction. And what we mean by that is an oceanic plate made up of basalt, sediments, and lithospheric mantle dives down beneath a lighter plate. Can be another oceanic plate, or it can be a continental one. And when that happens, the material that makes up that subducted plate starts to change and it dewaters. So some of the basalt and the sediments release that water. It filters upwards into the mantle above the subducting slab, and it reduces the melting temperature and causes melting. And then what happens is that melt is migrating upwards in a series of conduits, and it eventually will hit the upper plate, the base of the lower crust, and that is the part that we're really interested in, because we're trying to understand how you go from melts in the mantle all the way up through the crustal column into, eventually, volcanoes at the surface.
So, do we first get pools of liquid magma forming at the base of the crust?
So, as you go up through the crustal column and above the upper mantle wedge, there are these horizontal boundaries, and one of them is the moho, which forms the base of the continental crust. And that is one where we see, in particular, magma as it's coming up tends to pond and pool. Now, there's another kind of boundary that's steep and usually is characterized by fractures and fault zones and shear zones into which magma can also seep and migrate. But these horizontal boundaries and these vertical boundaries combine together to influence the shapes of plutons.
You mentioned the other kind of boundaries. Okay, you have the moho, which is, broadly speaking, following the surface at a certain depth. What is this other kind of boundary that you mentioned down at the base of the crust?
Continental crust, it turns out, has a very long memory. And so during past orogenic belts or events, and during past magmatic episodes, you create structures that become long-lived. So for example, in Fiordland in New Zealand, we can see some of these old structures. They're big, giant, steep zones, and we've been able to date them. They extend back hundreds of millions of years. And it turns out these are conduits or pre-existing ancient weaknesses along which rising liquids and magmas like to filter and penetrate. And they come up in these conduits and they interact with other boundaries like the moho, like other compositional boundaries, and they can fan out and form these mushroom shapes. But they originally feed up through these conduits that we can actually see.
So this magma that makes its way to the base of the crust, is it really entirely melted, or is it a kind of mixture of partially molten, partially crystallized? What would we see if we actually drilled the hole down there and had a look?
So if you could actually see it as it's coming up into the base of the crust and ponding, it would be a mixture of crystals and liquid. And the liquid we're seeing, the melts, are of an andesitic composition, so it's different than the original melts that were produced in the upper mantle wedge. And what that tells us is that magma is evolving as it rises, and so crystals are accumulating over time, and that liquid melt is changing. And what we're trying to figure out is how those crystals and melts interact, how those mushes, those magma mushes, are forming, how they change as they migrate up through the crustal column, and do they assimilate other material? And so ultimately what we're trying to figure out is what happens from that source of melt into those conduits, and as the melt migrates further, how they create magma chambers in the shallow crust that feed volcanoes. And that process is a combination of physical things that are happening and also chemical things that are happening.
That reminds me of one of the early GeologyBites podcasts in which I talked to Steve Sparks, and he talked about mush and was definitely a proponent of that model. Is that the prevailing view now, that we actually have this sort of part liquid, part crystalline mush in large volumes at the base of the crust before it ascends further up?
Yeah, so let's explore that a little bit. So let's go back to the older model, the one that predated the mush idea. So this older model is referred to as MASH. It's an acronym, and the MASH stands for melting, assimilation, storage, and homogenization. And in that older model, what happens is you get a bunch of magma coming in from the mantle. It gets injected into the base of the crust, and it starts to change, and it differentiates through a process called fractional crystallization. The other thing that happens in that model is it starts to interact with the host, the material into which it was in place. So there might be some melting of the host that gets incorporated into this magma chamber, and it changes its chemistry. And so that MASH model is really about how that one batch of magma starts to change, both in composition, and it starts to migrate out. Now that has fallen out of favor, and the new model is referred to as mush. It's not an acronym, but it kind of refers to that magma mush. And one of the main differences is it doesn't rely on that interaction with the host to change the chemistry. Another major difference is that it requires these multiple batches of magma, this mafic, iron and magnesium rich material coming from the mantle. It gets injected into the crust multiple times. And what that actually does is it reheats what's already there, that magma chamber. It mechanically mixes it, and it releases some of the trapped melts that are in there. And that, we think, is one of the major processes to produce granites, which then migrate to shallower levels and form some of these shallow magma chambers that feed volcanoes. So that's the mush model, and we see great evidence for that in Fiordland.
Okay, so let's talk a little bit more then about what we think happens next to go from the mush at the base of the crust and then cause the magma to rise up.
Yeah, okay, so let's get into some of the details of Fiordland. So one of the advantages we have in Fiordland is that the median batholith, especially on the western side of the province, is tilted, and it's very deeply exhumed. And the reason it's like that is because that piece of continental crust has been uplifted and eroded by motion on the alpine fault. And so the alpine fault is a plate boundary right there. It's got a big component of compression across it, and so it's resulted in this exposure. And so one of the things we can do in Fiordland is we can see those deep lower crustal levels. And in addition to that, we can see these individual plutons, these big giant bodies of magma where you can see the boundaries. And the unusual situation is we can see the top of them and we can see the bottom of them. And so we can actually walk physically from the bottom to the top and map the interior, the architecture of those plutons. So that's the basis for what I'm going to tell you about what actually happens. So we've been doing this for a little while, walking around Fiordland, and we've been able to find up to 5 of these very large vertical conduits, those kind of discontinuities into which magma from the mantle is intruding and forming these plutons. And we can see how it interacts with magma that is already in the lower crust. And one of the big things that happens is you get these multiple injections, and it starts to mechanically move some of the magma that's already there and release some of these granites. And these start to form intrusions and dikes, these steep-sided intrusions that start moving material from deep levels into shallow levels. And we're trying to trace, both chemically and through isotopic dating, but also through structures, physical structures. You can see we're trying to trace that path from mantle source all the way up through the pluton up into shallower levels.
What creates these conduits, and are they basically channels where there is more melt than there is in the surrounding regions?
The best interpretation we have so far is based on a long history of work in New Zealand, especially the South Island. And one thing we've discovered there is that the ancient continent of Gondwana, which New Zealand was a part of, was constructed by a series of terrains. Some of these were oceanic terrains that accreted onto the margin and sort of built out this continental crust of Gondwana. And during that accretion episode, you form these giant faults and boundaries between those terrains, and those persist in the geological record. And we found at least 3 of them. And you can see them physically, you can map on either side, you can see them chemically, how they're different on either side, and these seem to be the conduits that feed from the mantle all the way up into the upper parts of the crust. And what we see is these conduits, they're up to 5 to 10 kilometers wide. We see magma entering them as dikes and intrusions and start to spill out into the lower crust and then migrate into shallower levels.
You mentioned just a moment ago that you can see in the median batholith in New Zealand both the bottom and the top of these individual plutons. How do you know when you're at the bottom, and how do you know when you're at the top?
Over the past few decades, the geologists that have worked in Fiordland have been able to collect really accurate data on metamorphic pressures and temperatures. And these mineral assemblages, these metamorphic mineral assemblages, have been well dated. And so what that means is that we can take pressures, in particular, metamorphic pressures that have a certain time interval, so we can be sure that we're not mixing different time periods, and we can reconstruct what Fiordland looked like in ancient times, in this case, the Cretaceous, about 120 million years ago. And so based on those changes in metamorphic pressures, we can tell which way was down, which way was up. And it turns out, because of the mapping that's been done in Fiordland, we can see the base of these plutons and prove that it is, or it was, at lower crustal levels, maybe 45, 50 kilometers depth. And we can see the upper pluton, the upper part of that boundary, and prove that it was at shallower levels, maybe 25 kilometers depth. And so that full 15 to 20 kilometer thickness is visible and is well constrained by this metamorphic pressure framework.
And so if you were to go below the bottom or above the top, would you be moving into different rock types?
Absolutely. So at the top, it's very dramatic. You see all of this andesitic, dioritic pluton below, and then suddenly at the top you start moving into metasedimentary rocks that dominate the middle crust, and there's granites and all sorts of material up there, but it's a very sharp compositional boundary. And then at the other side, the bottom, you see the same dioritic or andesitic magma, and then immediately below it, you see these sheets of mafic and ultramafic rocks, stuff that was derived directly from mantle depth. So it's also a compositional boundary. So having those dimensions, having those exposures at the top and the bottom is a huge advantage and is allowing us to answer these questions in a new way.
And so you can go from the bottom to the top, you say, particularly in the median batholith in New Zealand, because it was tilted. Just talk to me a little bit more about how that geometry enables us to get such a good view of what's going on.
So if you actually look at a map of Fiordland, this is divided into these different provinces. And in a general sense, there's a western province and there's an eastern province. And what we've been able to show is that these provinces are bounded by reverse faults, faults where one part went up relative to the other. And if you actually walk from outside of Fiordland towards the Alpine Fault, you can see that those deep levels get more and more progressively exposed at the surface, and so you get deeper as you approach the Alpine Fault. So because the Alpine Fault itself has a component of compression across it, these thrust faults that we see in Fiordland seem to be genetically linked to the formation of that boundary. And so as we walk across Fiordland and these wedges of crustal material get popped up by these reverse faults, we can see deep into what was lower crust during Cretaceous time. So we're taking advantage of that sort of architecture and piecing back together what that magmatic arc, that Cordilleran-style batholith, used to look like.
And that tilting, then you say, is really a direct result of this location right next to this major fault plate boundary.
It is. And it's one of the big things that we have to focus on, even though looking at those faults and the origin of the tilting is not part of our current project. We have to address that because we have to be certain that we know how to reconstruct the crustal fragments into what they used to look like. So I'm a structural geologist, and so one of my jobs is to pay close attention to those faults and record how they're moving and how they moved in the past so that we can remove their effects and look at what that colony used to look like. So that's a big part of this project.
Have you been able to determine the three-dimensional shape of the batholith and then how that shape relates to what's inside it?
So doing that is very laborious. So if you look at Fiordland, and because of the results of the Alpine Fault, it is physically possible to walk from what used to be the upper crust down through the middle crust into the lower crust in a single traverse. But if you actually go to Fiordland, it is a temperate rainforest. It is covered by vegetation and deep valleys with moss and swamps, and the topography is extraordinarily rugged. And so practically what we have to do is we take advantage of the fjords. We hire a boat and we cruising up and down these fjords, which is a wonderful situation because the size of the fjords at sea level produce virtually 100% exposure of rock in a continuous way. So we can get these profiles. By going from fjord to fjord, we get these two-dimensional profiles deep into these exposures. But that's two-dimensional, right? We have to supplement that. So what we do is we take helicopters to the mountain tops, so above tree line, where there's also 100% exposure, and we do that across several ridges between fjords. And so we have data down at sea level that's continuous, data from the ridge tops, and we piece together this three-dimensional geometric model that provides the framework for the processes we're talking about.
And what kind of shape were you able to come up with if you were able to generate a three-dimensional shape?
We had some surprises there. So if you look at Fiordland from a map point of view, lots of these plutons kind of look oval-shaped or oblong, not quite circular. But if you look at the three dimensions, they have a distinctive mushroom shape. So when you look at the bottom and the top, you piece it together, it has this big giant flap, and sometimes one side is much, much bigger than the other. So it's kind of an asymmetric mushroom. And that flap of the mushroom is the part that goes laterally into the lower crust. And you can see that mushroom start to converge at the base of the Pluton into this steep, in the case of the Misty, a 5 to 8 kilometer wide vertical conduit. And inside that conduit, you can actually walk around in it. You see these vertical intrusions of mafic and ultramafic magma coming right from the mantle, and it's feeding into these mushroom shapes in the lower crust. Now, we did not know that going in, and you can't see that from looking at the map. You have to be able to reconstruct it from these three-dimensional architectural studies. And it turns out it's not just the Pluton we're looking at, the Misty, it's a bunch of these other ones too. So it seems to be a common pattern at the base of the crust.
So if you were to go from the bottom of the crust up to where the Pluton was in place, would you just have one big steep-sided conduit with a big mushroom, or does it kind of go through various conduit, mushroom cycles on the way up?
It turns out it's quite complex. So far, this is what it's looking like. So you do have these vertical conduits down at the deepest levels, and they feed these mushroom-shaped plutons. And the thickest one we see is about 15 kilometers thick, these mushroom shapes. and you can see the top. And as you go up through the top, you tend to get into more steep-sided zones in the middle crust. So it seems like you are feeding some of these steep-sided intrusions at middle crustal levels from these mushroom-shaped plutons deeper down. And then as you go up further through the column, it gets even more complicated, and you get shallow-level plutons, which can approximate circular objects or flat objects that can be quite complicated. And so it's kind of a mixed zone in the upper crust. And so it actually turns out that the lower crust, the deep parts, are actually more geometrically organized than it appears when you look at shallow levels. But you do go back and forth between these steep zones, the shallow zones, and back to steep as you're moving material towards the surface.
Do we have a sense as to the timescales involved? How long did it take to emplace the pluton, and how rapidly would the magma have risen up?
And it turns out it is, from a geological sense, much more rapid than we imagined. So this misty pluton, which is one of the largest in the medium batholith, it's about 700 square kilometers. And it's got a sister pluton called the Malaspina that's about the same size. And it turns out both of these were in place simultaneously in about 1 to 3 million years, which sounds long from a human point of view, but from a geological sense, this is very quick. We used to think it took 10 million years or more to build up some of these large plutons, but it's very quick. And you can tell this by dating zircons using the uranium-lead method. And also titanite helps to date some of these individual intrusions. So 1 to 3 million years seems to be the rule rather than the exception.
I'm reminded of a previous podcast in which I talked to Richard Ernst about large igneous provinces. I'm wondering if the magmatic flare-up that you're talking about here bears any relationship in scale or nature to the enormous volcanic outpourings of flood basalts that form the large igneous provinces.
There are some important differences. There's a couple similarities, but let's talk about the differences first. So if you look at the original definition of a large igneous province, it is usually thought of as a very large outpouring of mostly mafic magma. Magma like basalt that's rich in magnesium and iron. And it is on a scale, the largest ones cover millions of square kilometers. If you add up all of Fjordland, we're talking about thousands, and individual plutons are hundreds. So the scale is much less than a large igneous province, and the composition seems to be quite different. The similarity, however, is the pace at which these intrusions are building large piles of magma. So in some cases, large igneous provinces are in place very quickly, 1 to 5 million years, this huge outpouring in a very short period of time, forming these plateaus. They're immense, amazing things that can influence climate. And it looks like batholiths can also accumulate at speeds that are similar to those. Just the compositions are different, and maybe the scale is different.
You and your team have compiled a large body of observations in the field, in New Zealand, for example, but probably elsewhere.
Yeah.
Are you planning to tie all your results together with a physical model to better understand the way the various physical processes operate to create the plutonic rocks we see?
Yeah, absolutely. So in this project where we're looking at the misty pluton and parts of the medium batholith, we're in our second year. So we're getting ready to go into the field again next month. We're still gathering those architectural data, the samples we need to date things, to look at things geochemically. But we are building towards making a physical model and integrating that with the geochemistry to illustrate the processes of building plutons and how you make plutons and how you move them around.
Are there any particular outstanding questions that you're hoping the model will answer, or that you'd like to address with further field work?
Yeah, we want to really explore this mush model in more detail and see if we can track individual batches of magma. So just to remind you, that mush model requires multiple batches being injected, and we think we can track over time how they interact and how they migrate. The other part is we are now identifying large source regions of granite in the lower crust, and we want to track how that moves, both in terms of its speed, but also how it moves chemically, how it interacts with other batches as it moves up through the column. So we're collecting samples, creating the architecture, and we're now getting to the stage of doing isotopic dating to see if we can get rates and look at the chemistry to see how things are changing. So that's a major question. There's one other that I'm especially excited about. My colleague Elena Miranda is an expert on looking how things deform. So one of the things we'd like to get into more is to see as magma is moving, it is deforming. It can be brittle, it can be ductile, and we want to know the mechanisms by which that happens. And it turns out those mechanisms can change as you go from deep levels to shallow. And we have access to these very deep samples, and so we're now exploring on a micro scale how those minerals are deforming. And it has implications for many other fields, including how plate boundaries form, how shear zones behave, and all sorts of applications.
Keith Klepeis, thank you very much.
Thank you, Oliver. It's been a pleasure.
To see pictures and illustrations that support this podcast, go to GeologyBites.com, where you'll also find a subject matter index of all the episodes. There you can also give me feedback, which I welcome, as well as sign up to get my emails about new episodes.